Greetings, calculus students. This lesson is called First Derivative Analysis. It's the first of a series of lessons about how derivatives can inform us about the nature of the covariation between two variables, x and y, or inputs and outputs. In other words, as the inputs vary, how do the outputs vary? Such characteristics include whether the outputs of the function are increasing or decreasing, whether the slopes of the tangent lines are increasing or decreasing, where a function might have high points and low points, and what are its end behaviors. This lesson is specifically focused on how the first derivative informs us about the nature of a function. A critical number is an x-coordinate in the domain of f at which one of two things is true. Either f prime is 0, which means the tangent line has a slope of 0, so it's horizontal, or where f prime does not exist. This can happen where the tangent line is vertical, at sharp corners, or at solid endpoints. So there are two different types. We'll say where the tangent line is horizontal is type 1, and where f prime does not exist is type 2. Now looking at this image, looking for the type 1 critical numbers, I see 3 spots where the tangent line would be horizontal. At all these locations, f prime will be 0. So type 1 critical numbers are the x-coordinates of these locations. That would be 0, 2, and 3. Now for type 2, I see 3 sharp corners. A tangent line cannot be drawn at a sharp corner, and I see 1 endpoint that is solid. For the purposes of our class, we will say that the derivative does not exist at a solid endpoint, nor at a hollow endpoint for that matter. So this gives me 4 more critical numbers of type 2. Focusing on the x-coordinates, it would be 4, 5, 6, and 7. Over here we have a hollow endpoint. A location on a graph where there is no point cannot represent the location of a critical number because a critical number must be an x-coordinate in the domain of the function. So x equals -2 is not a critical number because -2 is not in the domain of the function. There is no point there. Next, we have a critical point is a point x comma y where x is a critical number. So we have a total of 7 critical points in this graph. Going in order from left to right, we have the point 0, -1, 2, -2, 3, 0, 4, -2, 5, -1, 6, -1, and 7, 1. Now the monotonicity of a function refers to whether and where the function increases, decreases, or remains constant. So beginning with this part of the function, as x increases, we see the outputs decrease until we get to this flat spot where we say the function is not decreasing because the graph is flat. However, after that, the function continues to decrease to this flat spot, and the function is neither increasing nor decreasing at this flat spot, after which the function will increase to this flat spot, after which the function decreases to this sharp corner, then the function increases, then the function remains constant. After this sharp corner, the function increases to this endpoint. I will highlight in red all the portions where this function is decreasing. Now I'll highlight in green all the portions where the function is increasing, and I'll highlight in orange where the function is constant. So we summarize that f increases for x in the intervals, focusing on the green portions, and give open intervals. When x is between 2 and 3, the function is increasing. Union when x is between 4 and 5. Union when x is between 6 and 7. Now f decreases for x is an element of, from -2 to x equals 0, the function was decreasing. Now at this location 0, the function is not decreasing because it is flat. So we have to break up our interval into this portion and this portion separately. So we have a union, and then from 0 to 2, and then a union from 3 to 4. And then f is constant for x is between 5 and 6. This is the only horizontal portion of the graph. Now, if f prime is bigger than 0 on an open interval, then f is increasing on that interval. If f prime is negative on an open interval, then f is decreasing on that interval. And if f prime is equal to 0 on an open interval, then f is constant, or a horizontal line on that interval. So in my drawing, I'm going to analyze where the sign of the derivative would be positive and where it would be negative and where it would be 0 without actually graphing the derivative. So I'm going to extend all the critical numbers down with these dotted lines, effectively breaking up our x-axis into 1, 2, 3, 4, 5, 6, 7 subintervals, namely these subintervals over here. Then I'll indicate what the sign of the first derivative would be for each of these subintervals. Everywhere the function is decreasing, we would have a negative first derivative. So the first subinterval, the second subinterval, and the fourth subinterval. The third subinterval, the fifth, and the seventh would have positive first derivatives, and where the graph is constant would have a 0 first derivative. Now, a local or a relative extremum. Extremum is a singular noun, not plural, which refers to a maximum or a minimum. So you could read this as a local or relative maximum or minimum will occur at a critical point around which monotonicity changes sign. And I'll add here, or at a solid endpoint. So looking at the signs of the first derivative, notice there's no change in sign from this first subinterval to the second. However, there is a change in sign from negative to positive. This suggests we have a local extremum. And in particular, it would be a local minimum because the function decreased then switches to increasing. Visually, a local minimum is simply a point that's lower than all other points in its immediate neighborhood. So in other words, if you look at only this immediate vicinity, this point is the lowest of its immediate neighbors, not necessarily the lowest of the entire graph. This is why we use the word local or relative, because relative to the immediate points next to it, this is the lowest point. Here we have another change in monotonicity sign from positive to negative. So the function goes from increasing to decreasing. This suggests the presence of another local or relative extremum. In this case, this would be a local max. And again, we say local because this point is the highest of all of its immediate neighbors, but not necessarily the highest of the entire function. We have another change in sign in monotonicity from negative to positive. So from decreasing to increasing indicates the presence of another local min. This point is the lowest of all of its immediate neighbors. From positive to 0 is not a change in sign. We need to go from positive to negative or from negative to positive. Same thing from this 0 to plus, suggesting that this point and this point are not considered local maximums or minimums. In the first case, this sharp corner is not higher than the points immediately to the right of it because of the horizontal line. And in this case, the sharp corner is not the lowest of all of its immediate neighbors because to the left of it, we have a horizontal line. And then at a solid endpoint, the function increased to this solid endpoint. So we do get to characterize this right endpoint as a local max. It is higher than all of the points immediately next to it. And we can only look to the left of it because there are no points to the right of it. Now this point on the left does not exist. It is not a local max because there is no point there. Now a global or absolute extremum is the highest point called a global or absolute max, or the lowest point called a global or absolute minimum over the domain. The absolute lowest points on this graph, and there's a tie, are these 2 points. They both have a y-coordinate of -2, which is the lowest y-coordinate possible. And the way we phrase this is we have a global minimum of y equals -2 at, and it occurs twice in this graph, at x equals 2 and x equals 4. Or you could simply say that we have 2 global minimums. One is at 2, -2, and the other is at 4, -2. Now how about a global maximum? Is there a highest y-coordinate of this graph? And due to the hollow nature of this left endpoint, the answer to this question will be no. If you pick a point on this graph and claim that it's the highest point, you can technically go a little bit higher. But that's not the highest point either because you can go a little bit higher. So there's always a point on the graph that's slightly higher. So the y-coordinate of 2.9 is not the highest because you can go y-coordinate 2.99. But that's not the highest y-coordinate because you can go 2.999, etc. So this function has no global max. In fact, note that the range of this function is y is anywhere from -2 included up to 3 excluded. This reveals to us that -2 is a global min, but there is no global max because of the exclusion of 3 in our range. As already discussed, extrema, both local and global, can occur at endpoints that are included. And notice this word, extrema. Extrema is the way to pluralize extremum. You can also say extremums, and that will be understood. The same is also true for maximum and minimum. Those are singular nouns, and their plural versions are maxima and minima, but also understood as maximums and minimums. Okay, the next several slides in this lecture will be given a function. We will find the derivative to help us analyze the monotonicity and to help identify any extrema. All right, let's go to the next page. Do a first derivative analysis of the given function. This means to find the following: all critical points, intervals where the function is increasing, decreasing, or constant, all relative and absolute extrema, and then we will confirm by graphing with technology. All right, the first thing you want to do when given a function is to determine what its domain is. Now the domain, I'll use capital D for domain, and a subscript to indicate of the function f, and because this is a polynomial, 4th degree, the domain will be all real numbers. There are no restrictions on what x's you can use in a polynomial. Now let's find the derivative. Using the power rule, we get 4x cubed minus 12x squared, and then the 20 will differentiate to 0. Well, the derivative is also a polynomial, so the domain of f prime is also all real numbers. Now, analyzing the domain both before and after differentiation is important because we're looking for any values of x that are okay in the original function, but that are no longer okay in the derivative. Such values of x would be type 2 critical numbers. But in this case, we have no change in domain, thus no type 2 critical numbers. In other words, there is no x that we cannot plug in to f prime that would cause f prime to be undefined for some reason. Also, keep in mind that polynomials are always smooth and continuous, meaning they will never have sharp corners, nor vertical tangent lines, or any kind of discontinuity. So in other words, if you begin with a polynomial, you will never have a type 2 critical number. So instead, we need to go looking for type 1 critical numbers, where the first derivative would be equal to 0. So I'm going to begin by factoring the derivative. A 4 and an x squared can factor out, leaving an x minus 3. If you were to set the derivative equal to 0 and solve, the factoring reveals that we have two answers. X could be 0 or x could be 3. I'll put my f prime notation back. These are type 1 critical numbers because they make the derivative equal to 0, and they are the only two values of x that do so. The next thing we do is we make a number line representing the domain of f. In this case, an entire number line from negative infinity to infinity. We put on it all critical numbers. Make sure you put them in order from least to greatest. This divides our domain into 1, 2, 3 subintervals. For each subinterval, we're going to pick a sample x value. So negative 1 is less than 0. Between 0 and 3 is 1. And more than 3 would be 4. And it doesn't really matter which test value you pick. And then we plug these into our derivative to see if the derivative is positive or negative. Most of this I would do in my head, but I will write down what I'm thinking. And I recommend you use the factored version of the derivative. So f prime of negative 1, plugging into the factored form, would be 4 times negative 1 parentheses squared, parentheses times negative 1 minus 3. I'm not going to actually multiply this out. I'm just going to keep track of the signs. 4 is positive, negative 1 squared will be positive, and negative 1 minus 3 is negative. And when you multiply a positive times a negative, you get a negative result. And that's all that matters to me right now. That f prime is negative on this interval. We can indicate this by putting a minus sign for this interval, which reveals to us that the function itself will be decreasing on this interval. Now let's test 1. F prime of 1 would be equal to 4 times 1 squared times 1 minus 3. Again, that's a positive times a negative. So again, we have a negative derivative on this interval. I can put a minus sign, which means that the function itself is decreasing. And now let's test 4. F prime of 4 would be 4 times 4 squared times 4 minus 3. Well, this will be a positive times a positive times a positive, which means f prime is positive on this subinterval. I'll put a plus sign, which means that the function is increasing from left to right. So in summary, f itself increases for x in the interval from 3 to infinity. This was the only interval where the derivative was positive, and f decreases, and then you want to express these two intervals separately, joined by a union sign. So for x is from negative infinity to 0, union from 0 to 3. Because at 0, the function is not decreasing, it's flat. That's why we just don't say from negative infinity to 3. Now this function is never constant on an interval. So it feels appropriate to say the graph is flat twice at 0 and 3, but never horizontal over an interval. Now we'll identify any relative and absolute extrema. The monotonicity analysis tells us that the graph will decrease, become flat, but then continue to decrease, and then become flat, and then forever increase. So I expect a basic shape to be something like this, a smooth, continuous function. The flat spot is not a local max or min, because that flat spot is not higher or lower than all the points in its immediate neighborhood. But at 3, we're going to have a local min. Also, this will be a global min. A point on a curve can be both. It can be both the lowest point in its immediate neighborhood as well as being the lowest point of the entire graph over the entire domain. Let's go ahead and find the y-coordinates of these two locations. We plug 0 into the original function, not the derivative. So I'm looking right here. Plug 0 in, we get 20. And now let's plug 3 into the original function. We'll get 3 to the 4th, which is 81. 3 cubed is 27, times 4 is 108, and then plus 20. So 81 plus 20 is 101, and then minus 108 takes me to negative 7. So in my little schematic, this flat spot that was not a local extremum is at 0, 20. And this flat spot that was both a local min and the global min is at 3, negative 7. Confirming with technology, I've typed in the function. I have this image. I'm going to change the y scale and draw attention to these 2 points, 0, 20, and 3, negative 7, confirming our work. All right, let's go to the next page. Okay, we have the same instructions. First, we give the domain of this function g, d sub g. Now we're going to square x and then cube root that. There are no restrictions on cube rooting, nor are there restrictions on squaring, so our domain will be all real numbers. Keep in mind that this is the same thing as x to the 2/3 power. So now I can find the derivative of g using the power rule. The 2/3 becomes a coefficient times x to the, and the new power will be 1 less than 2/3, which is -1/3. If I were to rewrite this, this would be 2 over 3 times the cube root of x. The negative power pushes the x to the denominator, and the 1/3 power is a cube root. Now here we do have a change in domain. The domain of g prime, x can no longer be 0. So we have to remove 0 as a possibility, writing that the domain is -infinity to 0, union 0 to infinity. That's because you cannot divide by 0. Well, we lost x equals 0. So 0 is in the domain of the original function. You can plug it into g, but you cannot plug 0 into the derivative. It makes it undefined. G prime of 0 does not exist. So x equals 0 is a type 2 critical number. And now we look for type 1 critical numbers. If you take the derivative and set it equal to 0, so we have 0 equals this fraction. And in general, if you have a fraction equals 0, that always implies that the numerator must be 0, which is what would occur if I chose to multiply both sides by 3 cube root of x. 0 times that expression stays 0, and the other side just becomes 2. But this has no solution because there is no x in the numerator. There's no way I can make this fraction become 0 by making a choice for x, because there's no way I can make the numerator 0 by making a choice of x. This means that there are no type 1 critical numbers. So next we do our number line that represents the domain of g, which will be all real numbers, and we put on it the only critical number we have, which is a type 2, which is at 0. This gives me 2 subintervals. The 2 easy test numbers are -1 and 1, and let's test them into the derivative. So g prime of -1 will be 2 over 3 times the cube root of -1. The cube root of -1 does exist. It's -1. So in the end, this will be -2/3. It doesn't really matter what the value is. All that matters is that g prime is negative on this interval. We put a minus sign and an arrow to indicate that the function is decreasing. G prime of 1 will be 2 over 3 times the cube root of 1, which is just +2/3. But what matters is that g prime is positive on this interval. Put a plus sign and a little arrow going up. So summarizing, this function g increases for x in the interval from 0 to infinity, and g decreases for x in the interval from -infinity to 0. We do have a change in monotonicity. The function goes from decreasing to increasing. Furthermore, the change happens at a location where g prime does not exist. Likely this is due to the presence of a sharp corner. Let's go ahead and find the actual coordinates of this point by plugging 0 into the original function. Well, that's the cube root of 0 squared. This will just be 0 in the end. So this minimum point is 0, 0, and it would be both a local min and would have to also be global, because a function that decreases forever to this point and then increases forever afterwards, this would have to be the absolute lowest point of the entire graph. Now in Desmos, to confirm, to do a cube root, you can look under functions, scroll to the bottom, and type this expression, make it a cube root, and then inside type in x squared, or you can type in x to the 2/3. This confirms what we suspected, a function that decreases to a point 0, 0, at which point there is a sharp corner. This is why the derivative failed to exist, and then the function increases forever after. Okay, let's go to the next page. Same instructions. This time we have a function h that is a rational function. It is a fraction of 2 different polynomials. So we begin with the domain of this function h. There's only one restriction. We have to avoid the denominator being 0. So x cannot be 1. So our domain will be everything up to 1, union everything after 1. Now let's find the derivative. This function is a quotient, so I'll think of it as u over v and use the quotient rule, which is u prime v minus uv prime over v squared. So we get specifically the derivative of the numerator is 1 times the denominator minus the numerator times the derivative of the denominator. Use the generalized power rule. So the 2 drops, the base stays the same. The new power is 1, which I won't write. And then also times the derivative of the inside, which is 1 in this case. So again, I don't need to write that. All over the denominator squared. So when you square x minus 1 squared, it becomes x minus 1 to the 4th. Now the first thing you should do here to simplify this is to do factoring. There are 2 terms in the numerator, and I see some x minus 1s in each term. So I'll factor out of the entire numerator, outside the red brackets, a single copy of x minus 1. That leaves left over this 1 here, which I don't need to write. There was a square on this x minus 1, and I took one of the x minus 1s out. So that leaves a single x minus 1, and then minus. This x minus 1 was factored out, so we're just left with 2 times x, all over x minus 1 to the 4th. Now I can do some canceling. This x minus 1 will cancel this power, reducing it to a power of 3. Now I can leave off the red brackets entirely. We have x minus 2x, that's negative x, minus 1, all over x minus 1 cubed. Now we're ready to analyze the domain of the derivative. Well, it's still the case that x cannot be 1. And this is the only value of x that will cause division by 0. So this is the only restriction. So our domain has not changed from the original. The fact that there's no change in domain from the original to the derivative means that there are no type 2 critical numbers. So if you were to change h prime to 0 and solve this equation, once again, we have a fraction here, and a fraction will only equal 0 when the numerator is equal to 0. So if I solve 0 equals the numerator, add x over, we get x equals negative 1. This is a type 1 critical number, and the only one. Okay, next we do our number line. This number line should represent the domain of the original function. Now the original function has a domain restriction, so we need to exclude 1 from the domain. Now the reason will be, this is a rational function. If you try to plug 1 into this function, you'll get 1 over 0. A non-zero over 0 in a rational function is an indication that there will be a vertical asymptote when x is 1. This automatically divides our number line into 2 subintervals. But in addition to this domain restriction, we also put all critical numbers, and there's only one critical number at negative 1. And now we have a total of 3 subintervals. Test numbers, I'll pick negative 2, zeros in between negative 1 and 1, and then 2. We plug these test numbers into the derivative. So h prime of negative 2. And I'm going to use this simplified version of h prime and keep track of the signs. So negative 2 is 2 minus 1 will give me a positive numerator. Negative 2 minus 1 is negative 3, and cube of negative 3 is negative 27. So I get a negative denominator. And a positive divided by a negative is a negative. So h prime is less than 0. I'll put a minus sign, indicating the function is decreasing. Now I'll test h prime of 0. Negative 0, 0, minus 1 is a negative numerator, divided by 0 minus 1 is negative 1, cube it is still negative, so we have a negative divided by a negative, that's a positive. So h prime is more than 0 on this interval, suggesting our function is increasing. Now keep in mind there's an asymptote at x equals 1, so this function will increase following the asymptote up. Now on the other side of the asymptote, we have 2 as a test number, so h prime of 2, plug it into the derivative. Negative 2 minus 1 is a negative numerator. 2 minus 1 is positive, and cube that stays positive. So we have a negative divided by a positive, that's a negative. So h prime will be negative, I'll put a minus sign, function will be decreasing on the other side of the asymptote. My high-level image of this now is a function that decreases, becomes flat, and then increases, and there's an asymptote. And on the other side of the asymptote, we have decreasing behavior. This asymptote is at x equals 1, and this flat spot has an x-coordinate of negative 1. We'll find the y-coordinate in a moment. So we can say that h increases for x in the interval from negative 1 where the flat spot is up to 1 where the asymptote is. And h decreases for all values of x up to the flat spot, so negative infinity up to negative 1, union, and then every x value after the asymptote, 1 to infinity. Let's go ahead and find that y-coordinate when x is negative 1. So h of negative 1, we are plugging into the original function h. We get negative 1 in the numerator. We get negative 1 minus 1 is negative 2, and square that is 4. So we have a critical point at negative 1 comma negative 1 quarter. And in the very least, we can call this a local min. Now, whether it's the global min is dependent on what happens with this piece over here. Another thing to be careful about, if you look at these arrows only, it'd be tempting to connect them into some sort of graph like this and conclude that we have a relative max here. But you must be careful. 1 is not in the domain of our function, and there cannot be an extremum at a value of x that's not in the domain of the function. So we'll have only one extremum at this point, and currently the best we can say is that it's local. We need more analysis to determine whether the extremum is also global. We'll do such further analysis in subsequent lessons. Graphing this function in Desmos gives me this image. Let me change my viewing window. I'll stretch out the y-axis and compress the x-axis. So we can more easily see we do have a vertical asymptote when x is 1, and then this relative minimum at negative 1 comma negative 1 quarter. Of course, at this point, we can now also conclude that this is a global minimum of the function. All right, let's go to the next page. Same instructions, new function. We'll begin with a domain of this capital F function. Now this function is a product of a part polynomial, part exponential. Both of these functions individually have domains of all real numbers. You can double any number, and you can do e raised to any number. So the overall domain of this function is all real numbers. Now let's find the derivative. This is a product of two non-constant functions, so I must use the product rule, which will be u prime v plus uv prime. So the derivative of 2x is 2 times the second plus the first 2x, and then the derivative of e to the negative 3x will be itself times the derivative of negative 3x, so negative 3e to the negative 3x. And now I recommend we factor our derivative. There are two terms. Each term I see a 2. Each term I see this exponential. So I can factor out a 2 and the exponential. I'll use some red brackets to keep track of my factoring. Both 2 and e to the negative 3x were factored out of the first term. That's everything factored out from the first term, leaving a 1 in that position. And then plus, the 2 was factored out and the exponential was factored out. So we have minus 3x. So I'll switch this to subtraction and put minus 3x. Now to switch the red brackets to normal parentheses. And here's my derivative factored. Now we want to find the domain of this. Well, this portion of our derivative is also a polynomial, so it has a domain of all real numbers. And this exponential has a domain of all real numbers. So the domain of the derivative is still all real numbers. So negative infinity up to infinity. There's no change in domain from f to f prime, so there are no type 2 critical numbers. So we now look for type 1 critical numbers. If I were to change f prime to 0 and solve, the factored version is helpful because I can set this factor equal to 0 and this factor equal to 0 separately, creating two different equations to solve. Now in the first case, I could divide the 2 away and then try to solve this equation. But if you recall, the graph of y equals e to the x is a function that has no x-intercepts. In other words, you cannot put a power on e and get 0 for y back. So in this case, you cannot pick an x that leads to an exponent that when you put it on e, that you'll get 0. This is not possible. In fact, e to any number is always positive. E to a number can never be 0. So we have no solution coming from this first equation. But the second equation, we can certainly solve for x. We get 1 equals 3x. Divide by 3, we get x equals 1/3. This is a type 1 critical number. Right? Next, we do our number line that represents the domain of this capital F function. It's all real numbers. On this number line, we put the only critical number, which was 1/3. So we only have two subintervals to test. A number less than a third, that's easy, would be 0, and a number bigger than a third is 1. And we test these into f prime. And again, I'll use the factored version. So capital F prime of 0 will be equal to 2e to the 0 times 1 minus 0. What matters is that we have a positive times a positive times a positive, because e to the 0 is also 1. So capital F prime is positive on this subinterval. I'll put a plus sign and an arrow going up from left to right. So the function's increasing. Then it's flat at 1/3. And now let's see what happens after 1/3 by testing capital F prime of 1. Plugging into the factored version, we have 2 times e to the negative 3 times 1 minus 3, which is negative 2. Now keep in mind, e to the negative 3, it's not a negative number. It means 1 over e cubed. So in other words, we have a positive times a positive still, but times a negative now. Overall, that's a negative, but capital F prime is less than 0 on this interval. Put a minus sign to represent that, and an arrow going down from left to right. So this function increases, and then it decreases. Capital F increases for x from negative infinity up to 1/3. Capital F decreases for x in the interval from 1/3 up to infinity. And I can conclude that we have an absolute max when x is 1/3. Let's figure out the y coordinate. Plug 1/3 into the original function. So you have 2 times 1/3 times e raised to the negative 3 times 1/3. That gives me 2/3 e to the minus 1, or you can write this as 2 over 3e. So we have an absolute max, or you can call this a global max, at the point 1/3 comma 2 over 3e. Let's confirm with technology. Here's a graph of our function zoomed in. We have an absolute max at this location in decimal form. Of course, we know that 1/3 in decimal form is 0.3 repeating. So we have a 1/3 x coordinate, and 2 over 3e is this decimal, of which we are being shown this many digits. This confirms that the function increases to our absolute max, and then after that forever decreases, following an asymptote. All right, let's move on to the next page. Now, a function that is continuous on a closed interval from a to b, closed meaning a and b are both included in the interval, which is why we see bracket and bracket, will have both an absolute maximum and an absolute minimum output. These absolute extrema will occur either at critical numbers in the open interval from a to b, so somewhere between a and b, or at one of the endpoints, so either at a or at b itself. Now, the theory behind this is simple. Let's say you have some interval from a to b, and the function is continuous on the closed interval, so we have to start at a solid point and end at a solid point. No matter how you connect these points in a continuous way, such as this, we'll have a global max here and a global min there, or simply a line, we'll have a global min at an endpoint and a global max at an endpoint, or something else, such as this, where we have the global min in between a and b, but then a global max at an endpoint. No matter how you connect these two solid points with a continuous function, you cannot escape the fact that there will be a global max and a global min somewhere. Find the absolute extrema for the function below on the indicated interval, confirmed by graphing with technology. All right, first let's analyze the domain of this function. Well, x squared has no restrictions, but natural log of x does. In fact, the argument of a log must be positive. So the domain of this function would be from 0 exclusive up to infinity. Notice, though, we're going to crop the graph from 1 to 3. Now let's find capital G prime. Derivative of x squared is 2x minus 8 times, and the derivative of natural log of x is 1 over x. So I'll put this 8 over x. The domain of G prime is still 0 to infinity. Now it's tempting to say that 0 is the only restriction in G prime, but you never want to expand the domain of G into a larger domain for G prime. The domain of G prime must always be some subset of the domain of G. It can either be equal to the domain of G or become smaller. You should never make the domain go larger when you find the derivative. So the only restriction is that x can't be 0 here, which wasn't in the domain of the original function anyway, so there's no change, meaning no type 2 critical numbers. So now let's set G prime equal to 0 and solve for x. We add the fraction over to the other side, multiply both sides by x, giving me 2x squared on the right side, divide both sides by 2, and then take a square root. Now normally I would say plus or minus 2, but our domain is only positive numbers, so the only answer here that matters is the positive answer 2. This function is continuous on its domain. In particular, the function is continuous on this closed interval. So we only need to evaluate the function at the endpoints of the interval and at any interior critical numbers. Of those outputs, the highest one must be the absolute max and the lowest one must be the absolute min. So we just have to evaluate g at 3 numbers. The left endpoint, capital G of 1, which will be 1 squared minus 8 natural log of 1. Recall that the natural log of 1 is 0, because 0 is the exponent needed on e to make 1, and so we get a result of just 1 here. Now let's find g evaluated at the critical number, g of 2. This gives me 2 squared minus 8 natural log of 2. I will reach for a calculator and give a rounded answer of about negative 1.545. Now let's find the value of g at the right endpoint of our closed interval. G of 3 will be 3 squared minus 8 natural log of 3. Reach for the calculator, and we get about 0.211. Now plotting these points, we have 1, 1, we have approximately 2, negative 1.545, and we have approximately 3, 0.211. The highest of these will be the absolute max, or the global max, and the lowest of these 3 points will be the absolute, or the global min. And I don't need to do any other analysis because it's guaranteed that the absolute extrema will occur either at an endpoint or at some interior critical point. And there was only one interior critical point, so we only had 3 points to test. Confirming with technology, here's our function. Let me crop it using curly brackets. 1 less than or equal to x less than or equal to 3 gives us this portion of the graph. And sure enough, we have a absolute maximum at 1, 1 and an absolute minimum at 2, approximately negative 1.545. This right endpoint is a local max, but is not an absolute max. Okay, this concludes our lesson on the first derivative analysis, which is the beginning of a series of lessons on using derivatives to help analyze the behavior of functions.